everybody, if you could please. So welcome again to another Del Mar College Department of Natural Sciences Friday Science Seminar. For those of you who don't know me, my name is Roger Steinberg, and I teach geology here. I'm very pleased today to welcome our speaker, Mr. Vernon Kramer, who also teaches geology here. Vernon is a native of Texas from Victoria. He worked for many years as a professional geologist. He has over 25 years experience in mining, mineral exploration, petroleum exploration. He's been all over the United States. He's worked in nearly 40 foreign countries. And considering his expertise on Mars, I'm thinking maybe he's worked on several different planets also. Vernon Kramer has been teaching here since 2004. We're very pleased that he's here. So if you would please, let's welcome Mr. Vernon Kramer.
The name of my presentation is Finding Useful Minerals and Mining on Mars Really Isn't All That Easy in that, as it seems. This will be part of a presentation that I gave at the 26th International Space Development Conference that was held in Dallas in May of 2007, last summer in here. This conference I was invited and it was hosted by the National Space Association or the National Space Society in here in association with the Mars Society in here. I gave this presentation as a representative of the Four Frontiers Corporation, of which I'm contracted as a geologist mining engineer, and my job is to go through and review the mining potential and the mining methods that we would use when we have a permanent Mars settlement colony here and we need to sustain the local economy there. I don't know, this was one of these real fortunate things I happened to get into. There are people on this that are from Africa, Europe, Japan, Australia, Canada, Mexico, South America. You see there from MIT, Stanford, all these various institutions, NASA, a lot of people in here. So, and nuclear engineers, habitat engineers. I just feel real lucky that they invited me to be a part of this group in here. On a personal footnote, when I got to go to that conference, I was really excited in there because I got to actually carry on 10 to 15-minute personal conversation with Buzz Aldrin, who walked on the moon with Neil Armstrong with Apollo 11. And I got to spend about 25 minutes with Harrison Jack Smith, who will be the only geologist to walk on the moon. That was Apollo 17. And while I was talking with him, I couldn't help it. I had to say something to him. I said, how tall was the average astronaut? Because he's about this tall. I said, about as tall as I am. And he said, you had to be because you couldn't fit in the capsules in there. So to be an astronaut, land on the moon, they're all about this tall. So that was kind of a fun thing. While I was there, I also got to spend quite a bit of time with Robert Zubrin. If you ever see anything on the television about the Mars and the Mars Society, he's the guy that has basically started it all. Talk about the Mars habitat there. I was supposed to go spend a summer ago, I was supposed to go spend some time with that. That's in, they have one in Greenland and one in Utah, but as it turned out, I was teaching and I couldn't go at that time. Another thing that was really cool is I got to meet this Steve Squires, and he invited me and some other people to go up to his room, and he had his laptop, and he had just got all the information from JPL, and he downloaded from his laptop computer in Dallas the program for the Mars rovers on Mars, what they were supposed to do for the next day. So that was really cool to see that actually happen from the location there in that hotel room in here. Also, I got to meet more than a half a dozen shuttle astronauts, and of course I was trying to say, would y'all give a talk at Del Mar and all this here? So maybe we can get some of those to come here in the next year or so, hopefully sooner than that. Why do I have an interest on Mars, which happens to be the fourth rock from the sun in here? Well, Margaret Mead kind of said it very well in here. She said that the traveler who has once been away from his home is wiser than he who has never left his own doorstep. Think about that. So I believe that one day we will be space traveling humans, and I want to be a part of the team that's left our doorstep. Now, for the first part of this presentation, I'm going to explain to you about what everything there is about Mars. Of course, when I gave the talk, everybody there was an expert on Mars, so I had to be very careful what I said on there. Okay, what are some of the basic facts about Mars on here? Well, this gives you an idea of the two of them side by side for actual scale comparison. And one of the things you'll notice in here that Mars is about 1/2 the diameter of the Earth. So basically that's the size of the iron core that's inside the Earth in here. Okay, it's about 1/10 of the mass, which is kind of cool because if you weigh 100 pounds on Earth, you weigh about 38 pounds there. So it's a good weight reduction place in there. Okay, it takes twice as long for the Mars to go around the sun. So basically their year is about twice what our year is here for far as Earth days go in here. But if we go and land on there, we don't have to make too many adjustments in here because one Mars day actually equals to one Earth day. So they're basically about 24 hours in here. You can see here that this shows the position of Mars in January with Earth in here and where they were in August in here. So you see if you want to go to Mars, there's a certain time you can go and a certain time you can come back. So John, if you're going to go there, it's going to be about a 2-year trip in here. So the closest that Mars ever gets is about 34 million square miles. Understand there's some pretty good, if you have a telescope, you can see the polar ice cap on Mars right now. And this is what we see in here. It actually has polar ice caps that are composed of water ice and carbon dioxide ice in here. And it's currently melting because of global warming. Roger keeps thinking it's because I'm driving my SUV up there every weekend in here, which is probably right. Okay, this gives you an idea here. I'm going to compare the Mars North Polar cap with the Earth North Pole. You see there's somewhat similarity to them in there. And we see here is the Mars South Pole cap, and it's almost very similar to the Earth South Pole cap. So you can see there's some similarities there. Not only that, I show you some frost that occurred on Earth in the morning. Guess what? On Mars we get frost also there too in the wintertime. So we're seeing a lot of similarities in here. Mars has a really thin atmosphere of carbon dioxide, which can create these planet-wide dust storms. In fact, it's just now getting off of one of these big planet-wide dust storms in there. And it's in the winter time that's going on in there. So the probes that we have in there are now having a little bit of a problem trying to get enough sunlight in here. Okay, there's actually, you may not be familiar with it, but there's actually dust devils on Mars. And here we see one coming right in through here. And this has been a very good thing for the Mars probes on here because they have these great big old solar sails on them, and they were getting dust on them, and the battery power the rechargeability was going down and down and down. And about every 5 or 6 months, one of these things go right over the top of it, and it now is back to 100% again. So, you know, it's real. We're kind of glad we have those things in there. So, you know, if you think that this is not much different than what we see right in here. Of course, with all this wind in here, we're going to have extensive sand dunes that we find on Mars, so you should expect to see that. As a footnote in here, the Mars atmospheric pressure is about 1% of Earth, so when we're there, we'll have to wear spacesuits, all this, and we got a problem with radiation we have to take care of. The atmosphere there is composed of about 95% carbon dioxide, which means I can use that carbon. And the composition is it does have a greenhouse gas. That greenhouse gas is called water vapor, and it's from about 0.03 to about 0.05% in here. Now you compare that with, you know, the humidity at Corpus Christi in the summer, which is 400%. I exaggerate only slightly if you ever tried to work out in here. Well, what's interesting in here, compare the carbon dioxide greenhouse gas on Earth is about 0.38% to about 0.05%. So the greenhouse gas on Earth is carbon dioxide, the greenhouse gas on Mars is water vapor, and they're both about the same percentages in here. Quick reference to the Mars equator temperatures in here. At the Spirit rover, they did get temperatures up to about 41 degrees Fahrenheit, but generally it was around 5 degrees, but rarely gets over 32. So it's generally going to be pretty cold while you're there. There's been various space exploration programs going to Mars. Without that, there's nothing I could do about planning a mining program or see what minerals there are in there. And so what I'm going to be doing is I'm going to be using the information from all of these probes and satellites that's gone around Mars in here. If you haven't gone to this, go to this. This is Google Mars. This is where this map is. So you just go in Google and type Mars, and you can actually download this here. They have Google Earth, well, Google Mars. It's a really cool site in here, and you can see lots of interesting things in here. One of the things you'll see in there is that there is some very high elevations in there. That one there is 66,000 feet, so that's about 15-mile high volcanoes in here. You also see a canyon in here that's about 1,000 miles long. It's pretty close to about 5 miles deep in here. And we also have some huge craters in here that will be a maximum of about 5 miles deep in here. What you see in here is two different scenes, and which one do you think was taken from Earth?
left-hand side.
Okay, let's see if you're right. There's the Earth and there's the Mars. So you can see if you're out from West Texas and you go to Mars, you think you're home in here. Looks quite similar in here. All right, since about 1960, 2/3 of all the space missions to Mars have failed. Only the U.S. has successfully landed functioning probes on Mars. Now, this is not exactly true because the Soviet Union had one that lasted for 8 seconds. So I'm going to exclude that one. I want it to last at least 10 seconds in here. Another thing, you know what NASA does is they send these probes up in here and then they contract them out. And one of the probes that they spent $500 million on in there, they gave it to this young engineer. He says, okay, now make sure you got everything go ahead and land it. He used the English system and everything was metric system and crashed it. And so we got all different kinds of mistakes that's been going on like this here. It's just amazing how we spend millions and billions on stuff like that in here. What was the first successful Mars landing in here? That would be the Viking 1. Here's an actual replica of it here. It landed on June in 1976, and Chrissy Planitia in here. And basically, they wanted to land it right in here at the mouth of this huge canyon here because one of the things they want to do is they want to test and see if there's any life there. Well, you can see it lasted for quite a while in here. And what did they see when they took the first pictures of it in there? They saw sand dunes. They saw strewn basalt rock, which is a volcanic rock in here. And maybe this didn't really come from a river in here. Maybe this actually came from an impact crater. So they were a little bit disappointed in that. They actually they had the arm that could go scoop out in there and get rock samples and soil samples in here. And you can see where they actually went and took the samples in here. And we got some chemical analysis of it. So now we got chemistry actually from the surface of Mars that I can do something with. They didn't find any water at this particular area in here. They also had a specialized test on there where they were going to try to find life. The first sign came in, oh, we think it's life in there. And when they went through, they discovered, well, maybe there isn't life there after all in here. So what they did said, well, everything's working perfect on this thing. Let's just go and start doing the atmospheric conditions and temperatures and everything else that we can do with this probe. And it would still be working today, but they had somebody go through and said, okay, go send this command. Did they check to see what it was? The command says, kill yourself. And that's what it did. And so we lost a $500 million probe because someone didn't check to see what was the command that they sent to it. And that was the end of that probe in there. Well, and in fact, we've got some of these satellites that go around there. They're so good now, they can actually, if they picked up the actual lander right in here, there's the heat shield in there and the parachutes from it right in there. So we know exactly that's where it's located right in there. Well, the U.S. was, of course, was afraid that the one would fail, so they sent a twin to it, and it landed 3 months later. It's landed right about in here. Basically, they thought this was going to be a nice flat area. You can see it wasn't quite so flat right in through here. It landed in September 76, and they didn't put enough insulation on this one in here, and they didn't put enough solar panels, and the battery failed, and it died after about, little less than 4 years in here. Again, they didn't check the arms. One of the arms didn't work, so they weren't able to collect rocks, but they did do about 8 different soil samples in here. And here we can see where they actually took the samples right in here. So now and it was basalt. It looked just like on the Viking 1, which is on the other side of the planet in here. So saying, well, everything was the same in here. So anyway, I got some information I can work with now, because remember, I have to do some mining planning in here. Okay, basically this probe tested but found no signs of life in the soil in here. One of the cool things it did take in here, it showed the picture of the summer and the winter time. These are the same exact areas, and we can see this is, they thought was mostly water ice with a little bit of carbon dioxide ice in here. Okay, the next successful landing will be in 1997, the Mars Pathfinder and a little rover called the Sojourner, and it's going to be landing over here close to the Viking lander in here. And look at the scenery in here. In fact, to me, it's amazing that they were able to land on something like that. Well, what they actually did, they had a little Sojourner rover in here that's going to go through and take some analysis and some other things in here that we're going to take a look at in here a second in here. What they did is they had an alpha proton X-ray spectrometer in here, and they noticed these were rounded river rocks in here, and they're composed of basalt, and for the first time, maybe andesite, which means maybe there's some differentiation going on way deep down in the Mars in here. So this is something we hope maybe it will or maybe it won't. Okay, from here we had chemical analysis of 15 samples of rocks and soils, and we could actually go through and determine the mineral content of these rocks right in through here. What happened in there is they didn't have batteries strong enough in here. It could not handle the cold. The transmitter couldn't, but the little rover kept on going. But it had no, and it was transmitting to the lander, and the lander didn't send the signals. And they think this thing went on for years. And they actually went through and took satellite pictures, and they saw where it was some way out in there, you know, trying to call home in here. Okay, there's even more data that's directly derived from the Mars surface that I can use for mining and planning purposes in here. And this is going to be from the two Volkswagen Beetle size. So these are huge machines in here. And they're named Opportunity and Spirit. And you notice in here it has cameras in here. That's about the height of a person in there. So it's as if you yourself are walking in here. That's why they deliberately put it that way. All right, these are virtual mobile labs that can do extraordinary feats, such as they can identify what they can dig below the surface. So, you know, if we have the satellites, all we can see is the stuff on top of the surface, which doesn't help me very much. But they can literally dig through the surface and see what's below there. Guess what? They're finding some different things in there. So this is going to help me find some minerals on Mars in here. That actually has a tool called a RAT, which is a rock abrasive tool, and it goes through and it grinds the rock in there so I can get rid of all the contamination in there so I can get a pure analysis. The problem we had with all the others is it had a lot of dust in there, and I really didn't know what I had in there. And it actually has a spectrometer in here that I can use to identify the actual rocks on the surface of Mars, and I can actually identify some minerals. This one here, for example, shows us some basalt, and we see a hematite that this thing could actually identify in here. And it actually has a microscope, so I can get some detailed pictures of what everything looks like in here. And of course, I use this to try to determine where that mineral is going to be useful or not for mining purposes in here. And the cameras. Look at the geological detail that we can get from that picture right in there. And this is going to be critical for me looking for areas that I want to mine in here. This is from the surface. So we got an incredible amount of information that's becoming available to me in here. We also have several orbiting rover satellites in here. I think this one just died. We have the European Space Agency's Mars Express, the Global Surveyor, and the Recon Orbiter in here. And what they're doing is they're doing spectra signatures, not from the surface, but from Mars. And you see here's the spectra footprint. What they're doing is they're trying to see what minerals are there, but it has to be at the surface, and it's like a relatively large area in here. So I can get some idea of what minerals are there for us to use, but it's kind of an averaged one. I can't get information like I can with those probes in there. Okay, so at least it can help me a little bit far as mineral exploration can go in here. For example, here was some of the things that thing identified. What we see in here, this is all false colored images, right? What it discovered was this huge area of hematite. So now I know that I have hematite, and what's going to happen is this is where we're going to put one of the probes in there to see if it was really there, and we'll see sure enough it is there. So this is what I can detect from from space itself in here. They can take incredibly detailed photographs of the Martian surface, and they can actually spot objects that's 3 feet across. Let's take a look at this one in here. For example, this is the chaos area in here, and this is one of the areas that we considered looking for minerals in here, and you can see this is going to be some really rugged terrain. But if you think that's a good picture, take a look at this one right in here. This is what the satellites out there are taking of. So we can see in here, we can actually make out layers of rocks right in here. We can make out landslides. We can see the lava tubes in here. We can see where the river channels went in through there. So there's an incredible amount of information that's coming from it. The bad thing about this is that a lot of this information they set up a contract with Johns Hopkins University, and they get first call on it. And they're using it for their graduate students, so I was really mad because they won't let any of the information go, so I'm having to try to pick out what I can from this in here. Okay, except for a few Mars meteorites, and we have those probes on Mars in there, there's little metallurgical or metallurgical knowledge that I can get from it, so I can do my mining plans. But we do have a few actual rocks. What happened is that a meteorite hit Mars, it ejected rocks way up into the sky, and they went into orbit and they landed on Earth. And what we see in here that so far the JPL says there's about 35 meteorites that literally came from Mars. How can we tell that? Well, we know by the chemical, by the isotope ratios in there. And so you can see what do they look like? They look like rocks that we find here on Earth, but these are actually from Mars in here. Okay, now all of that, I didn't deliver any of this. Everybody at the conference knew all this, okay? So this is to give you an idea about the planet that one day maybe one of you will go visit and possibly settle. Okay, now my job with Four Frontiers Corporation was to assume that once we arrive at Mars, it's not my worry how we're going to get there, how we're going to live. We got other people that take that. We have people, nuclear engineers, they're going to have the power plants, all this here. All right, we're going to settle in there, and we need to use the natural resources of our new home planet in here. And Mars is so far away from Earth that we cannot depend on stuff coming from Earth. We have to actually depend upon the minerals and the resources that we can find on this planet to sustain our settlement in here. So one of the things that we can safely assume in here that Mars basically contains a number of natural resources that's going to be of use to man in here. And of course, every element used by man is probably found somewhere here on Mars. The problem is where and how much of it is in there. And one of the things that was a problem when, before they hired me, they didn't realize this here, but there's a big difference between finding these elements and being able to extract these elements for our use in here. And this is a point that's often ignored by the people that are going to Mars, the moon, and go to asteroids, and they go to the other planets, and they, oh, we got all this stuff in here. Well, it turns out, no, it isn't quite that easy in here. What we needed to do is we need to locate the natural resources on Mars or any other planet that we can use to produce the metals and chemicals and glass and ceramics and all this kind of stuff in here. And they have to be specific type minerals that can do this. Of course, this is where the probes and the satellites are giving me some information that I can use here. So what you'll see on a lot of the talks about living on these planets and on the moons in here, there's a lot of commodity elements in here that we know exist on Mars. For examples, these are the alpha proton X-ray spectrometer. This is called whole rock analysis. What they did is they take that whole rock in there and they do an analysis on it. And we can see in here, here's the various elements. This is done by the soil, and 2 rocks done by the Opportunity. Here's another one done by Spirit. Here's another one done by Pathfinder in here. And there's the chemical analysis in here. And when you look at that, it says, wow, look at everything I have in here. There's all the raw materials I need for magnesium in here. I need that for metals and refractories and ceramics and chemicals. And there's aluminum. Look at all the aluminum, all the oxygen I see in there. I need that, for the metal, refractories, ceramics, chemicals. There's all the silicon I need to make glass, computer chips, all different kinds of chemicals. There's the sulfur that I can use for making sulfuric acid, various chemicals. And I don't have to worry about cement. There's all the calcium that I need in there for cement and all different kinds of chemicals. And look at all the iron in there. Just all you got to do is just go over there and just start melting it, and you've got everything that you want in here. But what they didn't realize is how did geologists go about getting these numbers in here? What these are called element value abundances, and they are assigned stoichiometrically to rock-forming elements, and they are normalized to 100%. So I may not actually have 4.9% in here. I had to normalize it in here to get everything to round out in here. And this doesn't show everything that's in there. We're just looking at some of the elements that we see in here. All right, you'll notice in here that if I take these oxide minerals, and what geologists do with this, they recast these things by calculating norms, and they have to take out several elements like sulfur and chlorine in here. And I can use that one, for example, and say, all right, this is what the rock ought to contain. It ought to contain that much orthoclase, this much plagioclase, the pyroxenes, the olivines, and the magnetites. Do those minerals actually exist there? I don't know, but they should. But that ain't going to be good enough. I'm going to need something better than that if I'm going to do some mining and planning operation. But you see, this doesn't faze the people that say, well, we go to Earth, we go to the moon, look at all the oxygen we have in there, look at all the aluminum we have in there. Well, no, it's not quite that easy in here. Okay, what's going to be important here is the type of mineral that you need. And the whole rock analysis gives me some general ideas, but I need better information than that in here. All right, by remote sensing, we already know of the Mars surface has minerals such as hematite. We also know it has mineral magnetite, which is an iron oxide. and groups of minerals that go by the name of olivine, which is a magnesium iron silicate, and plagioclases, potassium, sodium, calcium, aluminum silicates, pyroxenes. We know that it also contains hydrated minerals. What's hydrated? Means it has water with it, of gypsum. We know that it has epsonite, which is natural Epsom salt, which is a laxative, by the way. The kieserite, which is another form of magnesium sulfate. We also know that it has a complex hydrated form of potassium and iron hydroxide in here called jarosite in here. And we know we have phyllosilicates, which go by the name, we call them clay, they call them phyllosilicates. We're not sure whether we have montmorillonite or nontronite. We're going to see which one's kind of important to us here in a little bit in here. And of all these minerals that we have detected, now we got the probes on there, we got the satellites on there, which is the only mineral we have physically seen on Mars? And it turns out to be hematite. So I'm going to have to make a lot of assumptions on the stuff that I'm going to do here for my mining and planning in here. Well, of course, the presence of a mineral is not good enough in here. I have to be able to economically mine it. You know, I only have so many people, I only have so much resources, I have only so much energy, and I have to be able to do that. That's called economics in here. And I have to transport it back to the consumer, the one that's going to be in the community, and they're going to have to be able to take that mineral and process it and make our desired elements that we need out of it in here. So one of the things you're going to see right away, that the usefulness of a mineral commodity is going to depend how close it is to my community. It's not going to do me much good if it's on the other side of the planet, because I can't get to the other side of the planet very easily in here. So I want to stress that my job was to find the mineral and bring it to the community. I'm not worried about oxygen. I'm not worried about food, power, all this. We have other people that's going to do all this. They're going to take we will bring some water, and they're going to use the carbon dioxide. They're going to make methane. That's going to be a source of a lot of my power in here. So we have, and these people are really good at this kind of stuff. So we have other people studying this in here. Okay, so it's going to be somebody else's job to go in and turn it into whatever product that we want in here. Of course, a water source is critical in here. And if where's there water on Mars? Well, we know there's no surface water, but we did, with the probes in here, find a very large area in here that have hydrated minerals. Hydrated minerals means it's minerals with water in it. So I can probably heat it and get the water out of it. And you can see that over here where the opportunity is, there is quite a large area in here. So what I decided to do, well, is it really water in there? It turns out that the opportunity probe did confirm, yes, there are these hydrated minerals in here. So what I'm going to do is they actually wanted to go through and put the community in the bottom of this canyon in here because the atmospheric pressure was going. I said, well, it's not going to do any good. We don't have any minerals in there. How are we going to get all this here? So what we got them to change their mind, and we're going to go in and put a community that's going to be near the opportunity site in here. And that's because we have all these hydrated minerals. If we don't have water, forget everything else in here. Okay, right now we have a town site that's picked out over here near on Meridiana Planum in here, and it seems to fit the bill of everything that I wanted far as mining goes in here, and they seem to go along with it in here. Let's take a look at the opportunity probe site in here. We're looking at this part of Mars right in here. Here's a scale map right in here. This is the equator right in here. So the opportunity is just south of the equator. Recognize that that's highs and that's lows. So we're going from the highlands to the lowlands in this direction. There's your canyons right in through there. This one here is about 1,200 kilometers in here. Again, it's false colored, with this being higher elevations and the lower elevations. And we're talking about, there's our site right in there of where we would put our community in here. Again, a closer map in here. This shows these are about 600 kilometers apart in here, and so that's about 30 miles between where our town site would be and where the opportunity landed in here. Here's a colorized photo, gives you a little bit better idea of what the terrain looks like in here. Opportunity and the town site in here. Even a bigger map right in through here. Now this is where the opportunity landed. Actually, it's over here now. And right there would be where we plan to put the town site in here. So it's about 50 kilometers or 30 miles from that particular site in there. Okay, I want you to notice in there is a debris field that's around that impact site in here. And that's going to be a good thing. As we're going to see here in a minute, I do need the rocks that's coming from that debris field in here. All right, here's a topographic map that somebody in the company come up with in here. Here's the town site that they had planned right in through here. Now you see we have to have an area that's flat. That was a problem with the other town site. We couldn't go and land anything there. So this really fits the bill. They like that easier. They're rocket engineers we had. Well, we could probably go in and land our materials in here and bring it to the town site right about in there. And since we have rocks in there, maybe we can put part of it underground right in through here. Okay, for your opportunity, for your information, the opportunity is not as the original landing site in here. This goes to show you a map. Of course, I'm taking a lot of stuff that I'm for my planning is coming from this probe in here. Since it's landed, it's actually traveled about 7.2 miles. And in fact, when I was there, they were giving the commands to drive this part right in through here. It actually landed in Eagle Crater, stayed there for a while, took a bunch of chemical analysis, went to the Endurance Crater, did the same thing there, passed the Fram Crater, and now it's basically here at the Victoria Crater. So here we are looking at the Victoria Crater in here. This thing's about 2,000 feet deep. Wide, about 200 feet deep in here. And let me show you how good the photography is now. You can literally see from the satellite, there's the track that the rover took. It came back over in here and there, and there's the rover, and we can actually see the shadow from the mask that has the cameras on it. We're that good on it with these photos in here. So this is going to really help me with geology in too. All right, well, this is when it got there, it's getting close to winter time, and so they had to park it at a certain angle so to make sure they can get the maximum amount of sun in here so they can keep the batteries charged, and that's where it's sitting right now on the lip of that particular, I think called Duck Bay, and it's waiting for the summer. It can't do much now, so it's going to be another 3 or 4 months before we get much information out of it in here. So you can see I'm getting some really good, useful information out of this in here. All right, take another look at the town site in here. But remember, these are about 50 kilometers apart in through here. And why is this area again? Well, because this is where I know I have minerals. Now, I don't have to guess on it. I will pretty well know that I have the minerals in here, and they're going to be fairly close by. For example, if we take, remember the satellite photo we saw of the hematite field in here? All right, well, basically, the rover was sent here to investigate it, and sure enough, they did find the hematite that was proven right in through there. We'll take a look at that in a second in here. And so why not put the town site right about there? And the company agreed to it. That was probably a much better location in here. Okay, it turns out we need large quantities of iron and steel. Any society does in here. It's been used in all phases of our life, in all phases of our industry in here. It's just too much, we need too much iron and steel to bring it from Earth. It's just too far away, and if we're going to have a local self-sustaining economy in there, we have to produce iron from Mars. And this is going to be true on any planet that we go in here. Well, Mars is going to be a lot easier to do this than on the moon in here. Okay, what did Opportunity discover when they was driving around there? They saw these vast fields, they called them blueberries, in which we now know to be rounded masses of hematite, or which we call Hematite Spirals in here. And you can see there's incredible numbers of them, even inside the rock, but we see it's also loose there. To date, what do we know about these Hematite Spirals in here? Well, we know that they vary from about 1 millimeter to 6 millimeters in size, with a pencil eraser being about 6 millimeters and a pencil lead being about 2 millimeters. So you can see they're not that big, but they're big enough. Okay, what we find is these loose spirals are everywhere in this particular area in here, generally in the first 18 inches of the sand, and we actually find them loose on top of the rock in here. Some areas by the probe going around in various places, so there's some areas in which I have larger spherules and other areas where I have smaller spherules in here. So it's not consistent throughout the whole area in there, along the path of the probe in here. This is one place I definitely would want to avoid. This one here has a lot of rock fragments that's mixed up with the spherules in here, and that would be an impurity that I need to stay away from in here. Okay, here was another potential problem. In some of the areas in here, you see this, it's called a Dura Crust in here, and there's salt in here. And what's happening in here, if I get a lot of salt with these spherules in here, that's going to be another contaminant that I have to kind of stay away from in there. And this is a very good indication that there's salt right in through there. All right, now I told you what I know about them. What is it that I do not know about them in here? Well, is the iron content the same for all the sizes? Well, the preliminary indication said yes. There's basically, they're pure hematite in here. So, do I have some trace elements in there? Well, I may have a little bromine and some chlorine and some other things in here, but maybe that's not going to be a problem in here. What about, now here's one thing I don't know about, static electricity in here. You know, that was a problem on the moon. The suits were just covered with dust in here. Well, we think we have enough carbon dioxide in the air that maybe we can overcome this problem with static electricity charges in here. And then, of course, I have to find an area where I don't have many rock fragments in the spiral site, and I think I have found those areas in here. All right, so basically what the opportunity suggested is that we have these weathering right outside the rock in here, and these are basically called aeolian lag deposits in here, which are weathering from the rock and the wind's blowing the sand away. So this is what I mean by a lag deposit. It's in the fragments here, the spherules will stay there, and so I want areas where the wind's blowing a lot, because you see what it's doing in there? It's concentrating my spherules in here. So I definitely I'm looking for areas that look like that, and I can find them in here. Okay, take another look at our local hematite field location in here, and we're going to talk about mining this. How would I go about mining it? Well, I see there's a fairly rich deposit that's within 6 miles of our town site, or about 8 miles from our town site in here. Okay, well, what I have to do is, as a space geologist in there, I have to go out there and find the areas that have the highest concentration of hematite spherules and go through flagging. Aha, it looks like one there, I made this up, and there, and there, and there. So what I'm going is I'm finding the richest type deposits that I can find in that area, and that's what I have to have. Now we've done incredible calculations on this, of the mining and all the equipment and everything else, and I'm just giving you a real brief summary of it in here. We figured that we needed about 12 acres to which we can produce about 100 tons of spherules, which would yield us about 50 tons of iron metal in here. And because we have limited manpower in there, and machine size is going to be limited, and power is going to be critical in here, I've tried limited to 2 people that can do most of the operation in here, and I tried to find the most versatile equipment that we could possibly use. And it would be something like this. Now, we would have to, they've got people actually looking at designing these type things. We'd be in a cage, so we have oxygen away from radiation and all this kind of stuff in here. What it would do is that the driver of this thing would come in here and be able to scoop up, because he can visually see this in here, and get the highest grade type things, that these spherules, that he possibly can. We have another engineer that's looking at, but he thinks he can do it remotely. You'll have to prove it to me, but so we're looking at see if we can actually do this remotely in here. Okay, so why is it that I have to, now what I want to do is every time he scoops in here, I want to get the maximum amount of spherules I can in here. Why? Because we have to create that energy, which is probably going to be methane from the carbon dioxide and from the water. So the energy is going to be very expensive there. So I'm trying to use something that is cheap as possible for me to run and process in here. Well, I looked at various ways of getting rid of the sand and other particles. I talked to people that produce these trommels in here. What it is, it's a rotating cylinder in here. What you see in here, I come in here and dump the spherules in here, and this is mobile. I can move this around as I go around the various locations in here. The heavy rock comes in here, the fine grained sand goes in there, and there's the hematite. Now, I don't know what the dust factor was. In fact, when I was talking with the guy, we spent about an hour on the phone going through all the specs on it. He says, okay, when do you want it delivered? You know, he was ready to deliver it on Mars for me. But it was, I don't think he realized how much that would cost in here. Okay, now what I would do is I would not put it on the ground. I would put it in containers. And I'm going to use the container method on everything we do on Mars. The reason why, because I don't want to double handle anything. I want to handle it one time. And I want to make it so that it's easy to transport back to my community in here. You can see the kind of terrain he's going to have to drive over. And we've got people that are ready looking at making vehicles that can handle this. Now, all I'm going to do is tell them I want it there. You have to come up with the roads and all this. They think they can do all this electronically in here. Okay, well, basically the containers would hold about 10 earth tons, which is only about 3.8 Martian tons in here. And that I could, which will yield about, 5 tons of iron metal, and it would take me 15 days at 6-hour days. Wow, that's going to take about 6 months for us to get all the iron in there. Yeah, it sure will, unless you can get me a bigger loader. Well, I can't get that thing big enough on a rocket ship in there. Well, see, this is a problem that we have. Yeah, the action and reaction in here. So it will take us a long time to get this iron, but at least we can get it in here. Okay, so you can see the kind of terrain that we can drive over, and we think that, hey, if the rovers can do it, we can do it with our trucks in here. All right, now if the spherules have too many impurities, we'd have to do like it does here on Earth, where we have to go and crush it and process it and reconstruct it into pellets before we put it into the furnaces to make iron in here. On Earth, what do we use? We use bentonite clays, limestone, and dolomite, but we haven't found that yet on Mars. So if it turns out we have to reconstitute this, this is going to be a major problem for us in here. So that's why we need to get a sample and bring it back here. All right, that's a quick look at using hematite spherules and its potential problems and good points about it. But there's another source on iron that was discovered by the probes in here. And this is you know what they found? They found 5 iron meteorites on here. And these are the size of a basketball. So this is the first time we actually found a meteorite on another planet. Here's one right in here and right in here. So they haven't been looking for them. They just happened to accidentally drive past them in here. And I said, well, you know what? I think it would be worthwhile for us to find an inexpensive way, maybe balloons or something else that have magnetometers on it, and look for these large iron meteorites. So if there's small ones on here, there's going to be large ones. This will present a slightly different mining problem in here. Well, how large can these iron meteorites be? Well, if we look at the one in Hoban, Africa in here, this is 60 tons. There's a person standing right there, and there is an iron meteorite. Here's some others that would basically satisfy everything we need for 1 year. Right there, just that one meteorite. We can see here some others that we find on Earth in here, so there is a lot of them in here. And it's going to take me a different mining method to be able to cut these up and load them in here, but we can also get other metals such as nickel and other elements that are associated with these iron meteorites in here. Unlike Earth, you know, when we find them on Earth, they don't survive very long because they weather and they rust away. While on Mars, they'll probably last for hundreds of millions of years. So I'm pretty convinced that there's going to be some large ones out there. All we have to do is find them in our area in here. Okay, now what we're going to do is we're going to take a look at water, because that is absolutely essential for everything, for our population, for our industry in here. Remember I told you that we have this big, large hydrated mineral map that we see right in through here. Well, what do we have locally on the ground? Well, it turns out that the probes will indicate in here that there is lots of hydrated minerals all throughout these things. They'll actually go right up to these things and take all kinds of samples in here. And in fact, what did they find? This is how I came up with these names, because they got actual spectra of them. We know we have jarosite, epsonite, kieserite, and gypsum in here. And we're going to, since this is right next to my town probe site, I'm going to assume the crater right next to us have a similar type minerals in through here. And let's just take a look at what the opportunity came up with the Endurance crater in here. There's a picture of everything that you see right in through here. And guess what they found in there? That upper layer in there was 40% hydrated, that's rocks with water in it, and 11% hematite spherules. I'm not sure what I would do with that yet. And lesser jarosite. So we're getting about half of the rock there is hydrated minerals. There's my water supply right there. Okay, something else that was useful to me that I saw is in here is that when the probe went on top of the rocks in there, they found these things right in here. Well, they realized that this is from desiccation. What's desiccation? From the drying. So some of these, I don't have the full water content in here, but what is this doing? It's breaking up the rock. So this is going to be useful for me for as mining purposes go in here. All right, so this would be somewhere near our town site in here. I would go through, the geologists have to go through and find out where, anywhere in here is going to be the highest water concentration, and that would be the highest amount of hydrated minerals. That would be the area that we would mine first in here. All right, we went through all different kinds of things. One of the things I do not want to do is drilling and blasting. Too much energy involved, too much danger involved in that. And since these things are desiccated and broken up, why not use a ripper? We'd have to put, we can't go and ship one of these in there. We have to ship it in parts, and we can use rocks and everything else to put the weight in here. Why not go and, see, you have this big old tooth in here. It goes and rips all this up, and then I drive on top of it, and I break it up, so I don't have to use the dynamite in here. And then what I'll do is I'll either put this in containers, or if it's right next to the town in there, just truck it right to our water factory that we have in here for our water feeds stockpile in here. We estimated that we would need about 1,700 metric tons, would yield about 100 metric tons of water, or about 20,000 gallons of water on this. Now I'm using the low end. I'm going to assume that only half the mineral is going to be able to be extracted in there because of the desiccation that we see in there. Of course, that's a lot of material that I'm processing in there. We're going to have to use the same vehicles to get rid of this material. I can use it for a while, but not for not forever in here. So I'm going to have to, I can use the same equipment that brings it in here to take it out in here. What about all the hematite and the other minerals that are inside there? I don't have enough analysis to see if I can use that or not. So right now I'm going to plan that I'm not. If we're there, maybe that whole plan would change in here. Because the main thing is all I can do is estimate the type of minerals in there. So I'm going to have to find some high-grade gypsum or epsonite rock if I want a really large water supply in here. Okay, well, it turns out that the town site says that we may be adjacent to another resource in here that's not found in most of the hematite fields. And one of the things that you don't find in the hematite fields is you don't find basalt. Well, why do I need basalt in here? Well, see, this is actually a piece, this is called bounce rock. And they're convinced that that one came from that crater right in there. So there is some basalt right in through here. Well, I'm going to have to use this basalt in here. Why? It turns out, all right, this, we got a chemical analysis on this, and this thing is basically unaltered in here. And from the chemical analysis in here, I can actually make basalt glass fibers in here. We already have the technology. We're already doing it here on Earth in here. And of course, it's used for all different kinds of industrial purposes. You don't believe me? Just go on the internet and type in basalt glass fibers. And you can buy them all over the place in here. We actually can go through, they're stronger than carbon fibers, or they're about the same strength of carbon fibers, so I can actually go through and use it for reinforcement, so it's a little bit less steel that I have to use. I can use it for all kinds of fabric in here, for strings or whatever I have in here, and trying to make carbon fibers on Mars is going to be a real problem. But I can make these basalt fibers in here. Okay, and another thing in here, I need to have some hard rock if I'm going to make concrete in here. And there I have lots of it in here. So again, I would want to have somebody come through and pick out areas. I wouldn't want to go and pick the rocks up in here. I would want to go and pick them up in here where they're about the same size. I may need a screen to come in there and get to the proper size that we use as an aggregate for concrete in here. All right, we mentioned aggregate for concrete. Well, we also need sand. And sand is a little bit different beast that we see in here. What am I going to use sand for? Well, of course, I need it for cement and mortar. I need it for filtering water and other products in here. I also use it for, you know, if I'm going to pour metal, I have to have a mold in here. And one of the things that we're looking for is fosterite, which is an olivine sand. And guess what? We seem to have a lot of that. So that's going to be useful for us in here. Another thing we do is we put it in bags, we put it against the habitats in here, and there's a really good radiation and thermal insulation in here. So sand, we got lots of uses for sand in here. Potential sand problems again, here's our Dura Crust problem that we have in here. So we're going to have to find areas where we don't have that in here. What is some of the problems that we have with the Dura Crust? Well, here is in the U.S. where they went and used some sands, had magnesium salts in it, and you see what happens, the concrete falls apart after a very short period of time. So I'm going to have to make real certain that we don't have that problem in here. Okay, the opportunity, what it suggested just more recently in here is that the sand you see here is totally different than the sand that's coming from the rocks in here. So I may be able to find sand without the salts in it, and I may be able to get it looks like it has about the right sizes that I need for concrete and filtration and all this sort of stuff. So I'm encouraged by what we find in there. Again, I don't have enough statistics to actually go through and plan it, but I do have a plan of what I think we can do with it anyway in here. All right, now one thing we need to test on Earth in here, this is non-quartz sand, so it doesn't have quite the strength that quartz does, and we're using basalt that doesn't have quite the strength of quartz chert. So we'll have to go and test that here also. So we definitely need more test of our local sand in there. All right, now here's the one. This is the king mineral, as far as I'm concerned, of Mars. It's called gypsum because it can contain up to 20% water in here. This is a very critical mineral for our Martian industry and our society in here. It's like gold or silver is here. Okay, basically we use it for obtaining water. We use it for making sulfuric acid from the sulfur in it. We actually can go through and make lime, which you have to melt iron. And then we use it for making cement. And what's amazing, you actually not only use the calcium oxide for cement, you actually use the gypsum for making cement in here. Okay, and of course if you wanted to make sheetrock, which I don't think we'll do, but we could make sheetrock out of it in there. All right, now for it to be useful to me at all, I just can't have a little piece of gypsum in here. I need some pure gypsum in here. And that's one of the things that we haven't been able to detect right there where the probe landed in here. So this is going to be a bit of a problem in here. So to date, none of the rovers have detected a real nice thick deposit of gypsum. but that doesn't mean there isn't any in there. We have, remember I told you we got these satellite orbiters in there that can detect minerals from space in here, and guess what they found? They found in here, in this Juventina chasm that's right about in here, they found a huge deposit of gypsum in here. How big is that deposit of gypsum? It's 35 miles long, 14 miles wide, and 8,000 feet thick. And there for the taking, except it's in a 16,000 foot deep canyon. So that's a problem we have. Lots of it there, but it's unfortunately not in one of the best places there is. But it is there, so this is an encouraging sign. Also, there's indications of in the Aram Chaos area in there, and another one in this particular area in there. They found what we think is lots of gypsum right in through there. And if we look at the North Pole in there, there's lots of sand dunes in there. And guess what a lot of the sand is composed of? Gypsum. So we know that there's a lot of it in the general area in here. What about those near our town site in here? Well, we take a look at some of the mineral spectra signatures in here. I'm not going to go in detail with you, but I went through and looked at all these. There are areas which indicate there's pure kieserite. This is kind of stuff we can get from the satellites in here. All right, there's areas of pure kieserite in here and areas of pure gypsum in here. And all we have to do is take a closer look at it. Here's where we did some massaging of it, and we came up in this particular area. And here it looks like there's some fairly high concentrations. Now we're right in here, some fairly high concentrations of gypsum in here. This is why I get really mad at the Johns Hopkins University. They got all this information, and they're just not letting it out. And some of this information is a couple of years old now. All right, now here's what we'd like to find, something that looks like this. We find this in West Texas in here. This is known as the Castile Gypsum in here. Okay, now how this, it is a fairly soft mineral, although it's a little bit tough. I'm pretty sure because they do it out in West Texas, they actually mine it by ripping. So I can take a dozer and be able to rip it up because I want to do everything I can to stay away from mining and blasting in here. And then I would shred it, and then I would put it in a front-end loader, and then would put it into these steel containers, which would be trucked to our town site right in through here. All right, now once it's there, we're going to use it for lots of materials, as I showed you before in here. So this is going to be a very valuable mineral. Transportation is going to be a problem. I know, this is something else that we'll have to address in here. All right, now I want to point out to you that on Earth we never use gypsum for drinking water. We don't use it for sulfuric acid. We do use it for lime, though. And so technologies are going to have to be further enhanced. Here is where someone's come up with a design. This is supposed to be a hydrator that can successfully take the water out of the gypsum. So the technology still needs to be advanced on that one in there. All right, several times I talked about clay, how important they are to our Martian industrial basin here. The probes in there, they don't use the word clay, they use the word phyllosilicates, which are basically your sheets structured silicates in here. All right, what do we know about these in here? Well, here's where the probes have come up. Now, in the canyons in here, we do have some, which is supposed to be some sulfates in here, but you see in here, the red are the phyllosilicates. And right over there near my town site there is some. And then you see again, the probes indicate there's a hydrate, so I have my gypsum in there. So I have a lot of stuff, indication that maybe there is stuff over there. Okay, we do know we have huge concentrations of it in the chaos and in these two particular areas right in through here. Okay, but as far as the actual detection on here, we're going to see we're going to have to use the satellite, and it's not going to pick up that much, but it's going to pick up some in here. Our probes picked up some, but I need some higher concentrations than that. All right, what kind of clay resources do we have on Mars in here? They think there's two different kinds of clays in here. One's called nontronite. That's your iron-rich clays. We call it smectite. Very little use for us in here. What we need is the aluminum-rich clays, which are montmorillonites, and that's going to be the clay that we need to find in here. All right, assuming that we do find these in here, we're going to be using them for making cement. We need it for a binding agent. We need it for foundry sands. We're going to raise our own crops in there, so we need it for soil. And I don't know why we need it for a desiccant, because it's dry enough on Mars as it is in here. Okay, now here is the satellite picture, and what it's notice in here is it's looking for volcanic glass and clay, and these are pixels of where they have highest concentrations. The yellow is a low, this is a higher concentration. Basically the black, we don't have much data in here. So we can see it picked it up with a couple of pixels in here. So it must mean that there is probably some clay in that particular area in here. So this is within 30 to 150 kilometers away from me, so there is indication that there are these clay minerals here near to us. All right, so we have not picked it up with a rover in here, but when we do go in and find it in here, what we would do is use a ripper. Just like, see, I'm trying to use the same equipment everywhere in here, put it with a front-end loader, and then put it into containers and transport it into our community. We should be able to do that in here. All right, it'd be really helpful if we could find some quartz on Mars. And this is something that was a real shock to them in there. Oh, we're going to have all the glass in the world we want. There's all kinds of quartz on Mars. And I told them, wait a minute. There is no quartz on Mars. This hasn't been detected to date in there. And that really blew their mind in there. Well, if we do find it in there, we would use it to make glass. And the reason why we don't find a lot of quartz on Mars is because we don't have a tectonic plate environment. We don't have a subduction zone. And that seems like that quartz is intimately directly related to plate tectonics in here. All right, now they did go through and they found this rock in here called Fuzzy Smith, and it tested out 68% silicon dioxide. Oh, wow, we found quartz. And they put the instrument on there, no quartz. It's not quartz at all. They're not, but you see what they didn't put on there, they didn't put the ability to test opal or chalcedony. And this is what I think that we actually have in here. This is actually a form of opal or chalcedony that we cannot detect from, it's going to be such small deposits we won't be able to detect this from space. For example, this is West Texas in there. Here's your opal vein going right through there, size of pocket knife. We're not going to detect that from space in there. But I guarantee if we find it on Mars, we will mine it in here. Okay, now, just before the winter came, the Spirit drug through a particular area, and they found this white stuff in here. Oh my, this is about the time I was giving my presentation in here. And it's more than 90% silicon dioxide. Now remember, you got to be careful. That silicon dioxide, that's quartz. Well, what they're doing is they're casting these together in here. That's not what it really is. But anyway, they went through and ran it on quartz, and there's no quartz in there whatsoever. So this is what I think it may be actually, it may be opal or a chalcedony, because I checked to see they don't have the instruments that can detect that in there. But if we find this, we can use this stuff in here. All right, we need feldspars for ceramics, and they said, well, let's go and we need to make aluminum in there. And I really tried to discourage it. I don't think we want to go and find feldspars for aluminum in here. The main reason why is that we would have to take all of our nuclear energy just to make a few pounds of aluminum. Because making alumina is the most power-intensive metal that we can possibly make. So if you want aluminum, you better plan on bringing it from Earth in here. Why? Because on Earth, there's only one mineral that we actually produce bauxite from, aluminum from. It's bauxite. And how does bauxite form? In tropics. But we don't have any tropics on Mars, so we're not going to find any bauxite on Mars in here. Okay, but then they said, well, you know what? We can produce the U.S. They said, well, we could do it from feldspars. And they were citing this U.S. Geological Survey or Bureau of Mines study in which they produced aluminum from anorthite. No, they did a report. They thought they could, and they tried to do it, and all the pipes that have such strong acids, all their pipes were destroyed. They didn't even produce an ounce of it in here. Well, if we could get it from here, what we need to do is we need to use that particular mineral in here, but you see there's a problem. Feldspar is a group of minerals, and I have to detect this one, not these. And that's going to be a real problem in here. Okay, but if we do see in here, here's a Plagioclase Feldspar Map that we see in here, and we can see there's a few pixels of stuff that's been detected in here. I can't tell you what the feldspar type is like in here, but we see here it all is within our community. We definitely have to go there and take a look at it. But if it's anorthite, again, I don't think we've got enough energy to go through and produce the aluminum that we needed in here. Okay, this basically covers the list of useful minerals that we've detected on Mars. We've actually detected small concentrations of bromine. You know, one of the interesting things is this X-ray alpha proton X-ray spectrometer can't be used to detect salt. But we know that we have salt all over the place because we can see the little hopper crystals of it in there. We know that we have zinc in here. We know we have copper in here. We know we have nickel in here, bromine. We have lots of elements in here, but the equipment there can't detect exactly how those minerals are there and how we can be able to extract them in there. All right, this stage of exploration, I don't have enough data to accurately plan for mining or extraction, but I do have some general ideas. So I went through and planned how much we would mine a day, what kind of equipment we did, how far we'd have to transport it, what the processing is. So this is a real detailed presentation that I presented to the Four Frontiers Corporation in here. And they wanted a general plan, and we put it. And they had to change their entire everything, because they didn't realize, they thought, oh, you know what they thought they could do? They can just go get the soil in there and produce everything they want. There's oxygen, iron, nickel, cadmium, everything they want in there. And I said, okay, go out in your yard there. How come no one's mining your yard in there? It's got all that stuff in there. And then they realized that, no, this doesn't work in here. Okay, I want to acknowledge the personnel of the Four Frontiers Corporation, the various space and Mars agencies, including National Aeronautic and Space Administration, the Jet Propulsion Laboratory, Arizona State University, Johns Hopkins University, American Association for the Advancement of Science, European Space Agency, and all of the other agencies that provided pictures and data from the internet, which I use liberally for this nonprofit educational presentation. Okay, and thank you for attending.